Right, so this is a quick introduction to the lab for the embedded system class. So it's an introduction to this lab. And here's the final result. It's a 3-bit 2's complement adder and subtractor. If I send a 1 here, so this switch controls if this is a subtractor or adder. Okay, if I give a 1 to it, it's a subtractor. If I give a 0 to it, it's an adder. And it's a 3-bit adder and subtractor, so that's why I got A0, A1, A2, B0, B1, B2, like that. All right. If I have 001 plus 001, this is what I'm getting, which is 2, because it's adding, right? If I turn on this switch, it should be a subtraction, and I should get 0 over here. Okay, so it's a 0. And if I have 1 minus 2, plus 2 should be 3, minus 2 should be minus 1, and 1 minus, let's get a 4 here. So it's a minus 3. If it's adding, then it's 5. Okay, and the LEDs are showing the results at the same time as well. So if you see 1 plus 1 is 2, and 1 minus 2 is minus 1, right? That's why it's showing 1, 1, 1 here. 1, 1, you know, whatever how many ones you have is always minus 1 for 2's complement, right? And if I have 1 minus 4, 1 minus 4 is getting minus 3, and this is minus 4 plus 1, which is minus 3. Okay. Let me see. If I want to have 2 plus 2, no, 2 plus 1 is 3, 2 plus 2 is 4, 2 plus minus 4 is 2 plus minus 4 is minus 2, right? So it's getting the correct result here. All right. So make sure you can display both minus number and plus number over here, and also show the final result on the LED as well. Okay, so that's the final result. You want to demonstrate the same result on your basis 3 board. Okay, and now I'm going to give you a quick introduction regarding the theory running behind this application. Okay, it's called a little calculator. So first, you need to know how to get the overflow bit, the controller. You know, because you want to tell the IPGA board when it's adding, when it's subtracting, right? Still, the schematic of the 3-bit adder subtractor is like this. I just name it as C minus 1, C0, C1, and C2, S2, S1, S0. Okay, and you want to turn on the subtractor's function by giving a 1 or 0 to the control bit. I'm going to show you the schematic really quick. It's A1, A2, and here's a control bit here, and you have 2 options, which is 1 and 0, right? So it's going to switch in between these 2 numbers. If there's a 1, so 1 XOR A, you are getting, if A is 0, it's a 1. If A is 1, it's a 0. So it's if you have a 1 here, it's actually inverting A0, you are getting a A0 not, right? And if you have a 0 here, 0 XOR something is still something, right? So the A0 is being passed to this pin. So you are having an adding operation instead of the subtraction. And since these are the final 4-bit result, okay, but when there's an overflow happening, you want to directly use this C2 to form this 4-bit result. Keep in mind, if overflow happens, you want to directly use C2. If no overflow happens, then you want to use S2 as C2. So you just want to duplicate S2 here to form that 4-bit result. Okay, remember, this is how we want to get the correct result for the 2's complement, adding and subtracting. So let me give you an example over here. So if overflow happens, right, you want to adopt C2. So for example, 111 plus 100. This is n plus n, and it's 110. So it's getting a p here. So definitely overflow happens, right? And so when overflow happens, you want to directly use C2. So C2 right here is 1. Okay, let's see. This is minus 1, and this is minus 4. You are supposed to get minus 5, and let's see if this is minus 5. So this is minus 8, this is 2 plus 1, so eventually you are getting minus 5. So this is a correct result. Okay, in 2's complement, if overflow happens, you want to directly use C2 for the result, for the final result. Okay, so C2 is valid. So if no overflow, for example, 111 plus 101, it's getting a 0, 0, and it's 1, 1. So this is 1, so that's why it's considered as n. So it's n plus n getting an n. And so no overflow, right? So because overflow only happens when n, you're getting a p, or pp, you're getting an n, right? But now it's n and n, so there's no overflow. So what you want to do is you want to toss that one and duplicate this one over here to form that 4-bit result. Okay, because this is minus 1, this is minus 3, you are supposed to get minus 4, okay? And this is exactly minus 4, so the result is correct by doing this. But this, this is not a very good example because it's a 1 here already is getting a good result. But sometimes you can get a 0, and so you have to do this kind of operation over here. Let me show you another example to get a better idea on what's happening over here. So for the following one, overflow happens. 001, 011 plus 011, it's p plus p, right? 0, 1, 1, so you're getting an n here. So how do you want to put it as a C2 location here? Overflow happens, so C2 should be used, right? And this is 3, 3, you should get 6, and this is exactly 6. So the result is correct. And for 111 plus 001, what about this one? So 0, 0, 0, it's minus 1 is 1, right? So got 0. But the C2 becomes 1, and because this is n plus p, so there's no chance there's overflow happening. So you should toss this 1 and adopt the 0 here. You're getting 0, 0, 0, 0 is 0, which is the correct result. All right. So this is how you manipulate all the bits to get the correct result. It's not very difficult to do it in Verilog and on FPGA because you know all the logic functions to get the C2 equals what, C1 equals to what. You can find them, right? Just from the Slider's logic equations. So you need an indicator to show, like if overflow equals to 1, then do something, right? And if overflow equals to 0, then do something. So 1 means overflow happens, right? Like a flag. And so when overflow is 1, you want to adopt C2. So the final result, right? Let's call it digit. You should give just C2, S2, S1, S0, right? You have to combine them together to form that 4-bit result. If overflow is 0, so what you want to assign to the final result? So you want to toss C2 and use S2 as C2, right? So you are getting this. This is in Verilog how you form these 4-bit results. So here's a question here. How could you know if there's an overflow or not? We can do it over here because we can look at the NN got P, PP got N, we know there's overflow. But on the FPGA, how can we implement it in digital circuits or in the digital logic instead of, by looking at it, since there's no way we can look at it on the FPGA, right? So the way to do that is we can use actually C2, C1, this 2-bit binary number to find out if there's an overflow or not. So the combination of C2 and C1, there are only 4 combinations, right? It can be 0, 0. And so if C2 and C1 are 0, 0s, then there are 3 cases may happen. For example, if the 3-bit number, 2 numbers are 0, 0 for the MSB, whatever are here, I don't care. Okay, if these 2 addends are being added together, because C1 and C2 are both zeros, which means C1 is over here, right? And C2 is over here. So actually you are getting 0, 0 for the final result. I don't know what are these 2. I don't even care right now. So if I'm getting 0, 0, this is definitely a P, so P is P, 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 so there's no overflow, right? So no overflow in this case. So I'm just looking at the MSBs, all the different combinations for the MSBs of the 2 addends, okay? And the second case is, so 0, 0, and there's another case which is 1, 0, so there's a 1 in one of these 2 addends, and I don't care about these 2 digits. And C1, C2 are still zeros. Okay, so if I have 0 here, then 1 plus 0 plus 0, I'm getting 1. So it becomes NPN. So definitely there's no overflow, right? So what I'm doing is I'm trying to find out the logic from the C2 and C1, these 2 binary numbers, and the overflow indicator. So the last case is definitely 1, 1. I got 2 1s for the 2 MSBs. So N, and let's see, it's 0, 0, right? So 0, 0 is impossible because if I got a 0 here, it's 1 plus 1 is getting a 2, so C2 must be 1. So this is totally impossible. So this won't happen, right? So the second case is C2, C1 becomes 0, 1. And now let's go through all these 3 cases. 0, 0, it's 1, 0, right? 1, 0, it becomes 1. So overflow happens because it's a P plus P, or getting an N here. So there is the overflow. I just read an OV here. So the second case is 1, 0. I don't know, what are these 2? And it's 1, 0, which is possible, but there's no overflow, right? Or 1, 1, added together, and 1, 0 here, which is impossible because 1 plus 1 plus 1 is getting a 1. There's a carry out here. So for the next case, I'm having C2, C1 equals 1, 0. So the first case is 0 plus 0, right? And it's 0, 1, which is impossible for this case. So this just won't happen. And the second case is 1, 0. It's a 0, 1, which is impossible as well. and then I got 1, 1, and it's 0, 1, which is possible because it's 1, 1, 0 is getting a 1, so 0 here, so overflow happens, right? For the last case, C2, C1 equals 1, 1, so 1, 1 here, impossible, and 1, 0, it's a 1, 1, which is, possible, but there's no overflow, right? Because it's a n plus p. 1, 1, and 1, 1, it's getting a 1, so there's no overflow. So when we are looking at all these C2, C1 combinations, overflow happens here and here, only 2 cases, right? So if you write down the logic equation, C2, C1, and OV, you're getting 0, 0, 0, 1, 1, 0, 1, 1, all these different cases. So it only happens when C2, C1 is 0, 1, and C2, C1 is 1, 0. But all the other cases, there are no overflows at all. So if you look at this logic, actually OV equals C2 XOR C1. So that's the overflow indicator you want to get. So since all these inputs are given, so you can definitely find out C2 and C1s, and then you use this logic equation to form the overflow indicator. So you can use the if statement to do this, to combine or reforming all these different 4-bit results based on the overflow indicator's condition. Okay, and you want to show the results both on the LEDs and also on the 7-segment displays. Okay, so feel free to ask any questions you may have, and I hope this will work on your side. Thanks for watching.